Laplace transform of elementary functions, learning objectives. At the end of the topic, students are able to: first one, recall and write the formula of Laplace transform of elementary functions. Second one, apply the formula to obtain Laplace transform of given functions. By using definition of Laplace transform, we can find Laplace transform of some standard functions. Case 1, Laplace transform of function e raised to at when a is constant. Let f of t equal to e raised to at. Put this value of f of t in the definition of Laplace transform, that is L of f of t equal to integration 0 to infinity e raised to minus st f of t dt. We get Laplace of e raised to at equal to integration 0 to infinity e to the power minus st into e raised to at dt. Simplifying the right hand side, we get Laplace of e raised to at equal to integration 0 to infinity e to the power minus in bracket s minus a into t dt. After integrating the right hand side with respect to t, we get Laplace of e raised to at equal to in bracket e raised to minus in bracket s minus a into t upon minus in bracket s minus a when t running from 0 to infinity. Put the limits of t in the right hand side, we get Laplace of e raised to at equal to e raised to minus infinity upon minus in bracket s minus a, then minus when we put lower limit of t equal to 0, we get e raised to 0 upon minus in bracket s minus a. But we know that value of e raised to minus infinity is 0 and value of e raised to 0 is 1. So that Laplace transform of e raised to at equal to 1 upon s minus a. This is the standard formula of Laplace transform of function e raised to at. When we replace a by minus a in this result, we get Laplace transform of e to the power minus at is equal to 1 upon s plus a. Remark, if we substitute a equal to 0 in the above result, we get Laplace of e raised to 0 equal to 1 upon s plus 0. But we know that e raised to 0 is 1, so that Laplace of 1 equal to 1 upon s. Case number 2, Laplace transform of standard function sin at and cos at. First, let f of t equal to sin at. Put this value of f of t in the definition of Laplace transform. We get Laplace of sin at equal to integration 0 to infinity e to the power minus st sin at dt. Using the formula of integration e raised to ax into sin of bx dx is equal to e raised to ax upon a square plus b square in bracket a into sin bx minus b into cos bx. By this formula, the value of integration of right hand side with respect to t is Laplace of sin at equal to in bracket e raised to minus st upon square of minus s plus square of a into bracket minus s into sin at minus a into cos at when t running from 0 to infinity. After putting the limits in the right hand side, we get Laplace of sin at equal to 0, because when t is upper limit infinity, e raised to minus infinity is 0. Minus when t equal to lower limit 0, we get e raised to 0 upon s square plus a square in bracket minus s into sin 0 minus a into cos 0. But we know that sin 0 0 and cos 0 is 1. Therefore, Laplace of sin at equal to a upon s square plus a square. Similarly, Laplace of cos at equal to s upon s square plus a square. Case 3, Laplace transform of hyperbolic sin at and hyperbolic cos 80. By definition of hyperbolic function, hyperbolic sin 80 is defined as e raised to 80 minus e raised to minus 80 upon 2, and hyperbolic cos 80 is defined as e raised to 80 plus e raised to minus 80 upon 2. Now Laplace transform of hyperbolic sin 80 is equal to 1 upon 2 into Laplace transform of e raised to 80 minus e raised to minus 80. Separate L operator inside the bracket. We get 1 by 2 in bracket L of e raised to 80 minus L of e raised to minus 80. So by using the standard formula of Laplace transform for e raised to 80 and e raised to minus 80 derived in case number 1, we get 1 by 2 in bracket 1 upon s minus a minus 1 upon s plus a. Simplifying the right hand side, we get Laplace transform of hyperbolic sin 80 equal to a upon s square minus a square. Similarly, we can determine Laplace transform of hyperbolic cos 80 equal to s upon s square minus a square. Case 4, Laplace transform of t raised to n. Let f of t equal to t raised to n. Put this value of f of t in the definition of Laplace transform. We get Laplace transform of t raised to n equal to integration 0 to infinity e raised to minus st into t raised to n dt. Integrate this right hand side with respect to t by substitution method. Here we put st equal to x, from this t equal to x upon s and dt equal to 1 upon s dx. As t tending from 0 to infinity, we get x is also from 0 to infinity. By making this substitution in the right hand side integration, we get Laplace of t raised to n equal to integration 0 to infinity e to the power minus x in bracket x upon s bracket raised to n dx upon s. That gives 1 upon s raised to n plus 1 into integration 0 to infinity e to the power minus x into x raised to n dx. But by definition of gamma function, integration of 0 to infinity e to the power minus x raised to n dx is equal to gamma of n plus 1. Therefore, Laplace transform of t raised to n is equal to gamma of n plus 1 upon s raised to n plus 1. Now Laplace transform table. List all above derived Laplace transform formula in tabular form and remember it. So we derived the Laplace transform of these some standard functions using definition of Laplace. We treat this list of formula as Laplace transform table, and these are required to find the Laplace transform of some examples. Now illustrations. First one, find Laplace transform of e raised to 5t plus e raised to minus 60. First of all, separate L operator to each term. We get Laplace of e raised to 5t plus e raised to minus 60 equal to L of e raised to 5t plus L of e raised to minus 60. So use Laplace transform of e raised to 80 and Laplace transform of e raised to minus 80 formula from table to write the answer of these two. So Laplace of e raised to 5t is 1 upon s minus 5 and plus Laplace of e raised to minus 60 is 1 upon s plus 6. This is the answer to the given question. Second, find Laplace of e raised to minus 10t plus sin 3t plus 9. Separate L for each term. So we get given example equal to L of e raised to minus 10t plus L of sin 3t plus L of 9 into 1. By using table, the Laplace transform of e raised to minus 10t is 1 upon s plus 10 plus Laplace of sin 3t is 3 upon s square plus 9 and plus 9 into Laplace of 1 means 1 upon s. This is the required answer. Example 3. Find Laplace of t cube plus sin 5t into sin 3t. In this example, first of all we simplify sin 5t into sin 3t using trigonometric formula so that adjust to in numerator and denominator. Sin 5t into sin 3t equal to 1 by 2 in bracket 2 sin 5t into sin 3t. That gives 1 by 2 in bracket cos of 5t minus 3t minus cos of 5t plus 3t using the formula 2 sin A sin B. That gives 1 by 2 in bracket cos 2t minus cos 8t. Therefore, Laplace transform of given example equal to L of t cube plus 1 by 2 in bracket L of cos 2t minus L of cos 8t. Using table, Laplace of t cube is gamma 3 plus 1 upon s raised to 3 plus 1 plus 1 by 2 in bracket Laplace of cos 2t is s upon s square plus 2 square minus Laplace of cos 8t is s upon s square plus 8 square. That gives gamma 4 upon s raised to 4 plus 1 by 2 in bracket s upon s square plus 4 minus s upon s square plus 64. Now example 4. Find Laplace of hyperbolic 6t plus cos square t. Separate L operator for each term. Laplace of hyperbolic sin 6t is 6 upon s square minus 6 square from the table plus Laplace of cos square t. First simplify cos square t, that is cos square t equal to 1 plus cos 2t upon t 2. Separate L operator. So that gives 6 upon s square minus 36 plus 1 by 2 as it is, Laplace of 1 plus Laplace of cos 2t. From the table, Laplace of 1 is 1 by s, Laplace of cos 2t is s upon s square plus 4. Therefore, Laplace transform of given function is equal to 6 upon s square minus 36 plus 1 by 2 in bracket 1 upon s plus s upon s square plus 4. So, by knowing the method of finding the Laplace transform of these few examples, and remember the table of Laplace transform and apply that table to find the Laplace transform of these 5 examples. So this is the assignment to you people.